Hello and welcome to STAT 441 at Virginia Commonwealth University. This lecture discusses one of the discrete distributions called the Poisson distribution. Poisson distribution is a probability distribution named after the French mathematician S.D. Poisson, and it provides a model for the relative frequency of the number of events that occur in a unit of time or a given area or a given volume. So basically, it models the count of something over a specified unit, and it could be time, area, volume. Here are some examples which will which we have a Poisson distribution, and then we are looking at a discrete random variable in each of these cases. So the first example here is the number of new jobs submitted to a computer in any 1 minute. So the number of new jobs is the discrete random variable, and again it is a count of the jobs over a time frame which is 1 minute. Okay. Next example, number of fatal accidents per month in a manufacturing plant. Again, number of fatal accidents is the count over a period of month. So again, this is a discrete random variable, and this will follow a Poisson distribution. The third example is number of visible defects in a diamond. So here again, the diamond is the area, and the number of visible defects is the count or the discrete random variable. So these variables will follow the Poisson probability distribution, and then we can find the probability for a given value of y. Here is a summary of the characteristics of a Poisson variable. So if we have an experiment that consists of counting the number of times y, so this is our discrete random variable, the count of something, a particular event that occurs during a given unit of time or a given area or volume. So that would be the first requirement. Then the probability that an event occurs in a given unit, again we have a time, area, or volume, is the same for all the units. So if the probability of something occurring in the first minute is same as the probability of it occurring in the second minute and third minute, and so on and so forth. And also these units are mutually exclusive of each other. The number of events that occur in one unit um, is independent of the number of events that occur in the following unit. So the number of defects in the first minute is independent of the number of defects in the second minute. Okay. So if we have an experiment which follows these conditions, then the probability distribution can be defined by using a Poisson random variable, and the probability for a given value of y, okay, so number of counts is y, is given as lambda raised to y e to the negative lambda divided by y factorial. So in this case, the y can be a value starting at 0, 1, 2, 3, all the way up to infinity. So the count can be from 0 all the way up to infinity. And here, lambda is the mean number of events during a given unit of time. So for the Poisson probability distribution, we need to know the mean value to describe its probability distribution. The mean and variance of a Poisson distribution are simply mu equals lambda, and variance is also equal to lambda. So the standard deviation is square root of lambda. We will not look at the proofs of this, but we will just use these formulas for the mean and standard deviation of a Poisson random variable. Here are some histograms that show us the distribution. So this is when lambda is 1, this is when lambda is 2, lambda equals 3, lambda equals 4. This is uh, a pretty symmetric distribution here. Okay. Now let's use this information to solve some problems. So the first example here is about cracks in concrete. So let's look at the information. Suppose the number y of cracks per concrete specimen for a particular type of cement mix has approximately a Poisson probability distribution. Furthermore, assume that the average number of cracks per specimen is 2.5. Okay, so let's see if it follows a Poisson distribution. Although it's given, let's just figure out. So y is the number of cracks. So that's the count, and then per concrete specimen. So that's the specific area that we are looking at. And then each concrete specimen has to be independent of each other. The average number of cracks is lambda, which is 2.5. So the first um, concrete specimen has an average of 2.5, the second one has 2.5, they're independent of each other, and so on and so forth. So here are the problems that we need to solve, or the questions that we need to figure out. Find the mean and standard deviation of y, the number of cracks per concrete specimen. Then we need to find the probability that a randomly selected concrete specimen has exactly 5 cracks. So we can use the probability formula. Find the probability that a randomly selected concrete specimen has 2 or more cracks. Okay, so it could be 2 cracks, 3 cracks, 4, 5, all the way up to infinity. We'll have to figure that out. And then finally, part D is find the probability that y is between mu plus and minus 2 sigma. And then we'll compare the probability with the empirical rule to see if the values are close to 95%. Here's the first part, the mean and the variance of a Poisson random variable. We know mean is lambda, or 2.5 in this case. It's already given. So mu is 2.5. Sigma squared is also equal lambda, which is 2.5 in this case. So the standard deviation is square root of 2.5, which is 1.58. Then part B is where we need to find the probability that there are exactly 5 cracks. So this is the probability distribution for y. Probability of y is lambda raised to y e to the negative lambda divided by y factorial. So for this formula, lambda is 2.5, y is 5, and e to the negative 2.5 is 0.082085. So you basically use a calculator to get this value. Probability of 5, exactly 5 cracks will be 2.5 raised to 5, and then we have e to the negative 2.5 divided by 5 factorial, which gives us 0.067. So the probability that there are exactly 5 cracks is pretty small. It's only around 7%. Then part C is where we need to find the probability that a concrete specimen has 2 or more cracks. So we have to find the probability that y is greater than equal to 2. And like I said before, for a Poisson distribution, the possible values are 0, 1, 2, all the way up to infinity. So for y greater than equal to 2, we need to add the probability of 2 plus 3 plus 4 all the way up to infinity. Okay, now this is if we try to calculate this, it will be hard to do that. Instead of this, we can use the rule of complement. If for y greater than equal to 2, we can also write it as 1 minus probability of y less than equal to 1. Okay, so instead of adding all these up, what we do is we do a 1 minus probability of 0 plus probability of 1. Okay, so remember the complementary rule. So what is not here is here, and then we subtract that from 1. That would be easier to calculate. So 1 minus probability of 0, which will be 2.5 raised to 0 e to the negative 2.5 divided by 0 factorial plus, obviously, if we remove the parentheses, this will be minus 2.5 raised to 1 e to the negative 2.5 divided by 1 factorial. So solve this, we get 1 minus 2.87 minus, so total, which is 0.713. So the probability of y greater than equal to 2 is 0.713. The last part is where we calculate the values of mu plus and minus 2 sigma. So mu and plus and minus 2 sigma will be negative 0.7 through 5.7. Obviously, the possible values are 0, 1, 2, 3, 4, and 5 for this interval. And if we calculate the probabilities for 0, 1, 2, 3, 4, and 5 and add them up, we get 0.9581, which is approximately 95%. So it does agree with the empirical rule. And if you were to plot the distribution, this is what it looks like. So the peak is close to the mean value. It's close to 2.5. And then as we go further away from the mean, the probabilities become really, really small. Okay, so it kind of follows a normal curve or a bell-shaped curve. Here's another example using the Poisson distribution. US airlines average about 1.6 fatalities per month. Assume the probability distribution for y, the number of fatalities per month, and it can be approximated using a Poisson distribution. Here is what we want to find. What is the probability that no fatalities occur during any given month? What is the probability that one fatality will occur during any given month? And finally, the expected value of y, which is the same as the mean lambda and the standard deviation of y. Okay, so part one is where you're trying to figure out that y is 0, no fatalities. So our mean is lambda is 1.6 raised to 0 e to the negative 1.6 divided by 0 factorial. Remember, 0 factorial is 1. Okay, so that gives us 0.2019. So the probability that there are no fatalities during a given month is 20%. Probability that there is one fatality will be 1.6 raised to 1 e to the negative 1.6 divided by 1 factorial, so 0.3230. The expected value of y is simply lambda. So mu is 1.6, mean is 1.6. Sigma or standard deviation is square root of lambda, which is square root of 1.6 or 1.2649. Okay, so this is the Poisson distribution, another one of the discrete distribution. So remember, for this, we have to have a count of something over a specified area or time frame or volume. Again, this is a very useful distribution which we come across in very often experiments in real life situation. All right, so that's all. Thanks for watching, and we'll see you later.